Okay. Recently, I'm thinking of the meaning of the physics. I found that it's quite boring to do research in the scattering amplitude. What we do is just to write some boring papers. They're useful, the useless. Sorry, they're very useless. So I think why as a human, why we want to know the knowledge, why we want to study physics? That's because we just want to know how the world works, how the world how the world runs. We just want um, to establish the beauty of the world. Okay, so I want to do something uh, benefit, which is benefit to others. So I found that if you want to understand the quantum field theory and other uh, advanced topics in theoretical physics, you need to build up your math fundamental at first. And I found there is a good book that is topology, geometry, in physics. Okay, and it is chapter 9. Chapter 9, the fiber bundle. The fiber bundle the concept of fiber bundles can help us to understand uh, the field. That is because the field it can be regarded as a section of a fiber bundle. Okay, and uh, let's start. A manifold is a topological space which looks locally like Rm. Locally looking like the Euclidean space, but not necessarily as globally. Yes, globally it can have some non-trivial structure. So, when you want to study its local property, we need to introduce a chart. Yes. Okay. Then the chart can enable us to study the conventional calculus of several variables, and this is the definition of the manifold. Manifold is something that when you look at it locally, it is just a Euclidean space. Okay, but a fiber bundle is something that it is a topological space which looks locally like a direct product of two topological spaces. Yes. Many theories in physics, such as general relativity and gauge theories, are described literally in terms of fiber bundles. And let's begin. Uh, we will start with a simplest one, that is tangent bundle. We know that for a manifold M, at every point you can define the tangent space. Yes, then you just collect all the tangent space, that is P in M. So tangent space at P. This is the tangent space. This is a collector of a tangent space, and this one is called tangent bundle. Okay. Then we call the manifold M as the base space. Base space. We could choose an open covering of the M. That is, it is quite like the charts of the manifold. Okay, anyway, we choose UI as open. Sorry, let me make things PEN. It's an open covering on M. Okay. Then you have the covering, then you can define the local coordinates. Okay. Local coordinates. You notice it's quite easy. This is M. Okay. Just cover it. Cover it. This is UI. From UI, you can define a map from the UI to Rn. To Rm. The Euclidean space. That is for a point in the Euclidean space, you can define it by some real number. Okay, that is the coordinates. This is the coordinates of P in the manifold M. Okay. Then a vector at P belong to the tangent space at P. It can be written as that is the vector at P is V. Vector is there's no index. Vector V is equal to V mu at P. It has the local basis that is partial x mu at P. Okay, this is a vector at P. Okay. And here we require that the UI is homomorphic to Rm to some open set of Rm. That means it is a one-to-one map. Okay. Then the tangent space is the TPM. Okay, this one is TPM. You can see it is homomorphic to Rm. Okay. So you can see that let me see TUI can be identified with a direct product, that is R M times R M. Oh, sorry, this one should be phi UI, I think. Yes. Anyway, so it's quite easy. Okay. Then maybe we can draw a cartoon to describe the concept of bundle. That is, you just draw the base space with a none. This is M. This is UI. This point is P. Okay, P is here. This is a bundle. We denote the bundle as as E. It should have been like this. At every point P is sorry, let me see. This bundle we call it FP or something like that. I don't know. Sorry, I forget. Anyway, this is a bundle. It can be for the tangent bundle. It is just the tangent space at P. Okay. Anyway, then when you define a map, when you see that there is a vector at P, you just mean that you have a function from the point P to the bundle. Okay. Let me call it a section. It's a map. Okay. Then its inverse, we just call it it is pi. Okay. Any point on the bundle will map to its the point P. Okay. So we just call pi is projection. Okay. It's quite easy. Then what can we do? Then the things are quite similar to the manifold. When we consider we have two charts, we have two charts to describe the same region. That is, this is UI, this is UJ, and this is P. Okay. For P, this is a bundle FP. Let me see. It should be my P. Let me see. Yes, it's FP. This is a bundle at P. And FP is that is holomorphic to F as a bundle. F can be a vector space or any other things. Okay. This is F. Okay. This is another F. We need to give a coordinate. Sorry. For manifold, we need to give for every chart we need to give a coordinates to describe the point B, and for the bundle, a fiber bundle, we need another coordinates to describe the point on the bundle FP. Okay, FP is quite abstract. Okay, for example, FP is a vector space. Sorry, is not a vector space. It is something which is holomorphic to vector space. Then we need to attach it every point here with a real vector here. I should denote it as this one as what we want to do. So and this is what, sorry, this one is no co-trivialization. That is psi j. Okay, -1. Let me see. Okay. Psi is something. Psi is something from what to what? Here to what? No, I have made a mistake. This is not. This is just a psi j. Okay. No, sorry. I made a mistake. It is phi j inverse. Okay. Phi j inverse. This should be phi I inverse. Okay. Both the 2 point describe the same point on the bundle P. So there is a transition function between the two charts. That is from here to here, maybe from J to I. That is, it should be phi J equal with phi I inverse. This is a transition function from J's chart to I's chart. So it should be T I J. That means from J to I. That's great. Okay. Great. And you may need to denote that this the map depends on the point on the basis space, that is P. Okay. Good. We require that the Tij. We notice that for the vector bundle, the vector bundle means that F is a vector space. The map from F to F requires the Tij, the transition function, to be linear and smooth. Actually, we require it is a diffeomorphism. That is anyway, and because the two phi I, the phi I and the phi j are both diffeomorphism, so its composition is also diffeomorphism. The diffeomorphism from a vector space to a vector for itself is just a GL. the general matrix, non-degenerate matrix. Okay, we call it is a structure group. Structure group. Yes. No, not structure group. Anyway, for the vector space, we require you know that the transition function is just a matrix. But for the general case, we need to something act on F. On F. If F F can be anything. F can be a group, can be anything. If we have a group to act on F on the left, we just see the group G is a structure group. And the G should be a knee group. It's great. To describe what we see as a Fibre bundle, we need to denote this is a bundle manifold. This is a projection map, and this is basis the base space. This is a bundle, and this is a structure group. Structure group will act on the F on the left. That's great. And something in short, we use a shorthand notation that is E to N. Okay, that is a plan. That's great. I see. Everything is quite easy. So from the definition of Tij, you may can find some property, some conditions. For example, Tij, Tii. Tii is an identity map, and Tij is equal to Tji's inverse. That's great. And Tij, Tjk equal to Tik. That is from K to I, from K to J and from J to I is equal to just from K to I. It's great. Okay, it's quite trivial. Now what again? Okay, if a Fibre bundle is if a Fibre bundle is just a drag product, it's quite trivial. It means you don't need many charts to cover it. Yes, it's quite trivial. And then what can I do? Okay, let's end it. It's just a concept of the Fibre bundle.